let's finish up our discussion of Gauss's law and do some examples. So again, just to reiterate Gauss's law, so for any closed surface enclosing total charge Q in, the net electric flux to the surface is defined like this here. And so again, there's two sides to it. There's the integral, and then that integral, that surface integral, will always equal the charge enclosed over epsilon naught. So we're going to look at some examples today that actually give us a lot of insight into physical systems. And so first, I just thought we'd start here. This is a good conceptual question for people who are kind of mixed up at this point. So just think about this, and then we'll talk about it. Is Gauss's law valid for a square Gaussian surface? Yes, no, or not necessarily? What do you think? All right, hopefully you got yes. So Gauss's law works for any kind of surface. So it's a really powerful rule that works in any kind of situation, any kind of surface you can imagine. It's just that for us, the stuff that we can sort of use it to get some really interesting insights and stuff from usually involves stuff with a lot of symmetry, like a sphere or a cylinder or some sort of flat plate or something. So in those situations, we can usually get a lot of information. So Gauss's law always works, but there's a lot of cases where we can't really use it to really help us that much because it would be pretty complicated math. But in circumstances where that integral can be done easily or quickly, this can be really helpful. But it's just really important to remember that this always is true, no matter what the surface. It's just some cases are sort of more beneficial to us than others. And so the one we'll look at today, just to kind of finish up, is this idea of the E field from a point charge. So we had some point charge. We'll say that it's got a radius r and some charge q. And so last time we looked at this and we said for that r greater than big R. And so imagine that our r is over here, right outside of the point charge. We got our Coulomb's law. So kq over r squared. And so now what we want to do is say, well, let's look at this maybe, the same charge, or there's some sort of charge r, and let's think about the electric field at some radius inside of r. Okay, so r is less than r, and so if I drew this little, this box here, so again, we could again do this like we did before, where we broke the point charge into a bunch of little tiny pieces and figure out what the electric field is. But Gauss's law gives us a way that's just a little bit more powerful. And hopefully, this is the key. Hopefully you can see that due to symmetry, the field inside of here must point like this. All right, and so it's one of these situations where the electric field is constant, and the electric field is perpendicular to the surface at all points. All right, and again, if I just sort of blow up that, here's my point charge, and here's this special circle I'm looking at. If I just pick some point here, right now, and then just sort of maybe just draw a little line in here. So on this point, there's a bunch of charge above the point and a bunch of charge below, which could have, you know, if you write sort of our x-y axis, it could have an x or y component, but again, there's just as much charge up here as there is down here. So I'm going to argue that the electric field has to point this way here. Now, you could say that it points backwards. Okay, it ends up, if it's a positive charge, pointing this way. But either way, you would sort of get the answer to come out in the end. And the way I sort of reason that is, if you look here, you know, there's sort of more positive charge to the right of it than to the left, and so you can imagine it has to point this way. So you can look at one little piece there and kind of reason through, and then the thing is, since it's got this spherical symmetry, you can kind of rotate it, you know, sort of move this piece down over to here, and then argue, well, this piece must look like that. And so since all the pieces really are the same, and because of that symmetry, you can argue that the whole thing has to look that way. And so what I'm going to do then is go through here and just try to calculate the electric field inside this charge. And this is something that people do. And again, we can use this Gauss's law. So I'll draw my picture again. Here's my little r. Here's the big R. What we're going to use is this idea that rho is equal to charge divided by the volume. Now, for volume for a sphere, we recall that the volume is 4/3 pi r cubed. So this is our charge density, and this is the first one we used for a volume, I think. So it's q divided by 4/3 pi r cubed. And so if I do my Gauss's law business here, so for this side, it's just E times the area. Again, our Gaussian imaginary surface is this one here with a radius r. So there'd be E times 4 pi r squared. Again, this just boils down to electric field times area, since electric field is constant at this surface and 90 degrees to that surface. So this is the case where it's really helpful for us because you got some symmetry in there. It's really useful. Now the Q enclosed, essentially what we're going to try to do is we're going to try to figure out is sort of what percentage of the total charge is inside of here. That's the sort of business that we got to do now. So for Q enclosed, what I would do is I would take this rho, okay, so rho times the volume enclosed. Okay, and just as this is like unit analysis, so my rho, times volume enclosed, so rho gives me Q per volume. If I multiply by volume enclosed, it basically takes my Q and then multiplies it by the ratio of volume enclosed to volume total, right? Which hopefully, if you think about that, that's what is going to end up getting you, how much charge you have, right? If this sphere holds like 20% of the total volume, then it must hold 20% of the total charge. And so that's what we're going to sort of use here. And so if I plug everything in here, so for my rho, I'll plug this business. So I get Q over 4/3 pi capital R cubed, and then my V enclosed is just 4/3 pi r cubed, a little r. And so that's again this ratio of the volumes. And so here I can take this and just cancel out the 4/3 pi, cancel out the 4/3 pi. That feels good. And then if I divide by all this stuff, so E, my equation E will be 1 over 4 pi epsilon naught Q over here. And if I sort of cancel everything out because there's this factor of r squared here, there'll be r upstairs and then a capital R Q on r cubed on the bottom. Now, just typically remember when we're writing this, this is now E is a function of r, and so I'll just write this K Q R over r cubed. And so again, this is for the region when our radius r is less than r. And so what you'll see the book in some places do is they'll make little plots of like electric field versus the radius. And so the sort of point where it switches over is at capital R, and that's the point when you're outside of the sphere. And so you notice here that if I take this and plug in my capital R, so this is supposedly good for this entire inside region, I get K Q capital R over R cubed, which works out to look exactly like what you'd get for Coulomb's law, KQ over R squared. And so if I'm doing this as a function of R, in that inner region, it comes up to here, and it's nice linear, and then outside of here is we're going to go towards that sort of region where it's decreasing, goes as 1 over R squared. And so if we just sort of try to summarize this, then we get something along the lines of this here. So my electric field is a function of R. For this point charge, which we're treating like a sphere, you can look at either R bigger than the radius of the sphere or R less than. We've got two different answers. Both of them we could solve with Gauss's law, and then you can summarize this here as this plot of E versus R, and this is sort of capital R is the turning point. And so this is something that you'll do. We'll do this in discussion with another example. And so it's the kind of thing that you'll typically do in just good practice and using your Gauss's law. So let's look at one sort of a similar idea here. So a thin spherical metal shell of radius r carries a uniformly distributed charge q. It is surrounded by a concentric thin spherical metal shell of radius 2r that carries a uniformly distributed charge negative q. For which of the following regions enclosed by a concentric spherical Gaussian surface of radius r is the electric field 0? Answer all that apply. So this is a really good example. what I think a pretty tricky conceptual Gauss's law question. So it's completely conceptual. You can't really math your way out of this one. So please stop and give this one a try, and then we'll talk about it. If you get this one, then you are really at this point sort of have this stuff down. So go ahead and pause this here and give this a go. Okay, so hopefully you got these two here, r less than r and r greater than 2r. And so let's draw our picture. So if I have this right, there's sort of a small shell of radius r where we have q on that one, and then a bigger shell outside of here where there's negative q. Let me just make sure that that's right. So a thin spherical metal shell of radius r carries a uniformly distributed charge of q. It's surrounded by a concentric thin spherical metal shell of radius 2r that carries a uniformly distributed charge negative q. And now what you would want to do in these two cases is look at the different regions. And so you'll put a little Gaussian surface. So here's maybe my Gaussian surface 1 for that first region. Here's my Gaussian surface 2 for that second region, and then there'll be one out here. And the question asked, when is electric field equal to 0? Well, so in all three of these cases, all right, it's going to be E dot dA, and since they're all spherical symmetry, the electric field in all three of those cases has to be perpendicular to the surface and has to be constant. And so we can just do E times A, so that's really great. And so let's look at the three regions individually. So region 1, region 2, region 3. And so region 1, if I look here, again, from Gauss's law, so Gauss's law, this equals the Q enclosed over epsilon naught. So this is really all just about the Q enclosed. And so I get E times A, and for region 1, there's 0 charge enclosed, and so we get electric field would have to equal 0. So that's why it's one of the regions we picked. I'll jump to region 3, just because you can kind of do the same thing. At region 3, right, we've got this Q inside and a negative Q, so altogether it cancels, and so the same thing. So electric field would be 0. And of course in region 3, it's sort of like you're outside, in a sense, it's sort of like our model of an atom, right? You've got sort of two sources of charge. One is positive Q, one is negative Q. They're equal and opposite, and they're centered at the same point. So the electric field outside of that is 0. So that's kind of like that model. And then just technically, so region 2 is not going to work out that way. And so here, and I'll even just right here, so this point, we would write our surface density is 4 pi r squared. So this would be the r vector, or the r distance that we're looking at, and our charge enclosed at that point is just q. And so if I solve for that, I would get 1 over 4 pi epsilon naught q over r squared, which again I would just write as kq over r squared. And so we talked about this last time, but when you're looking at, they call it here the spherical shell of charge q, when you're outside of that distance, right, any spherical basically surface of charge whatever looks like a point charge of that charge, and that's what you get here. So in the middle region, it would just be sort of the point charge there. And so the thing is, hopefully as you do more of these, you can kind of get faster. But like I said, this is a super tricky problem when you're first starting out, because it's just completely 100% conceptual. There's really not much math here, and like I said, the math is not going to save you with this. So this is definitely one, if you're not getting it, ask questions so we can work on this in class. So now we're going to spend some time using Gauss's law. Again, we're going to find that some of the stuff we can do with it is pretty powerful in talking about conductors, and specifically conductors in electrostatic equilibrium, which will be something that we'll be interested in and we'll use a lot. So this is a conductor. It could have some charge on it, some excess charge, or not. And by electrostatic equilibrium, it means we've sort of let it sit there for a while, so it's had time to kind of rearrange itself. And the first thing that we're going to claim is this idea that there will be no charge inside a conductor. All right, and that sort of I'm sorry, there'll be no electric field inside of a conductor. And the rationale for that is that if there's electric field, right, the conductor has a bunch of free electrons. And so if there's any electric field, those electrons will move and distribute themselves. The charge is free to move around, and so it'll move until there is no force on it anymore. And when there's no force on it, the electric field will be zero. And so we're going to claim the first thing here, that our electric field inside a conductor has to be zero. So the next thing we can do with that is draw a little Gaussian surface around it like we did here. And since the electric field inside that surface has to be zero, right, then there can be no flux going outside of it. And so that implies that the charge inside has to be zero. So just sort of looking at the feature of conductors and then using Gauss's law, we can claim that, okay, the electric field inside a conductor has to be zero, and there can't be any excess charge there. And so if there is any excess charge, it has to reside on the surface. And then finally, next, the external electric field right at the surface of a conductor must be perpendicular to that surface. If it wasn't, if it had some sort of tangential component, it would exert a force on the surface charges and cause a current, and so they would not be in electrostatic equilibrium, they'd be moving. Okay, and so basically, two things here. We can, if there's any excess charge on the conductor, it has to be on the outside of the surface, and it has to be such that the electric field is 90 degrees to that surface. Because if not, then this electric field would be causing a force, and these charges would be moving. And so you can kind of sum everything that we know about a conductor and electrostatic equilibrium in this picture here. So basically, if there's any excess charge, it has to be on the surface. Let's see, we haven't got to this point yet, so we'll talk about this later. Electric field inside has to be zero, and the exterior electric field is perpendicular to the surface. And so there's so basically, if there is some charge on it, it's all going to kind of get pushed out to the surface, and it's basically going to spread itself out sort of nice and evenly to have some sort of distribution like this here, which can be, again, helpful to us in problems. We can sort of tell a lot about a situation by knowing this. And so here's another sort of example. And suppose we have some conductor that in this case does have some charge on it or whatever. All right, and it's got a hole in it. Okay, they'll sometimes call this a cavity just to be kind of, more fancy with it. But it's essentially a hole. If there's a hole there, okay, what we can do is we can set up a Gaussian surface like this here. Okay, so here's our imaginary Gaussian surface. And so what we can say here, so since we've got no electric field in the conductor, there can't be any flux going through this Gaussian surface, which implies that we can't have any Q enclosed. So the Q enclosed must be zero. And so if we have this cavity here, where there's no electric field inside the conductor, and then there's no charge on the surface of this cavity, of this hole, the electric field in the hole must be zero. So the E field inside this hole must be zero. And so this is a really handy fact, and you can use this to create what's called a Faraday cage. And suppose, here's a picture of a parallel plate capacitor, our nice constant electric field. Suppose you wanted to exclude the electric field from this region. What you do is you put a conductor in there, and give it just a little bit of time to reach equilibrium. And what basically it does is it arranges its charges. So it was like a neutral conductor. It arranges its charges in such a way that the electric field inside this cavity has to be zero. And so it's a way for us to exclude electric fields from a region of space, and this is called screening. So if you want to have some space where there's no electric field, you put a conductor there to screen it. And this conductor is sometimes called a Faraday cage. So these Faraday cages have many applications. Like one, Faraday cages are used in airplanes to protect the things inside, like people and fuel and electronics, from lightning strikes. You also have these days people using secure rooms that are Faraday cages that basically don't allow any electromagnetic radiation to come in from the outside. And we haven't talked about this fully yet, but we're going to find out that things like our cell phone, Bluetooth, all this stuff that we use for signals uses electromagnetic radiation. And so basically by excluding electric fields, you can create this special room where your cell phone can't get a signal in or out. And so any kind of device that might be trying to listen or whatever would not be able to penetrate there. And so there's lots of applications about Faraday cages. I'm going to post some demos on the website, so you can check that out. So please check that out. But now let's do maybe an exercise here. So here's a kind of problem you can do. So a charge of 3 nanocoulombs is put inside a cavity inside a hollow chunk of metal that is electrically neutral. The total charge on the exterior surface of the metal is what? And so this is something that's sort of going to make us think about how conductors work. So give this a go, and we'll talk about this in a second. All right, so I get 3 nanocoulombs. And so what we can do is we can look at a situation like this. So the way that it works when you have a charge inside that cavity, all right, we can look at it the same way. We can make our imaginary Gaussian surface here and say, okay, well, we know at this point of the Gaussian surface inside a conductor, the E field must be 0, so there's no flux coming through. So that implies the charge enclosed has to be 0. And so whatever Q you put here that's positive, your conductor is going to make a negative Q just at the surface right around it. So that, okay, remember, the only charge inside a conductor can be right there at the surface. And so what you can then do in a picture like this is say, okay, so there's 3 nanocoulombs. That means over here there's going to be negative charges. So this is a neutral conductor. Okay, now there's these negative charges will be a total of negative 3 nanocoulombs. Now if I'm taking that extra piece, those extra 3 nanocoulombs, that means we're going to be leaving behind some charge on the surface, and that would have to be a surface of 3 nanocoulombs. So the answer here is 3 nanocoulombs. So just to be clear, in a problem like this, okay, we put this extra charge in here because we wanted to see what would happen. And then we're using the characteristics of the conductor. And the idea is that this, again, so here's this cavity. So normally this was a neutral conductor, nothing going on. I put this positive charge here, and what it does is it pulls negatives, okay, away from nuclei. Those nuclei are going to be left without an electron. But what happens is because electrons move, so think about it. It might have been like maybe some, these charges happened sort of here in the middle of the conductor, maybe gave their electrons over. Well, then all of a sudden an electron from over here is going to jump over, and one from over here is going to jump over. And so basically they'll jump over until they can't move anymore, and when they can't move anymore, that's when they've reached the edge. And so all that positive will end up being on the edge. And so it's a little bit more complicated than we make it out to be, right? But the trick is that when we're all done, the charge will only be on the surface of the conductor, and then you can figure out what it has to be by looking at your picture. So in a case like this, if there's like this 3 there, then we know there has to be a negative 3 on the inside and a positive 3 on the outside. Okay, so send your questions in for class time, and we'll talk much more about this. Thank you.